Now let's take, the same example, and I have created here essentially a table form which helps us in explaining multiple different iterations. In the previous slides, we just looked into one iteration, and now let's look into the overall calculations in a tabular form that iteratively shows multiple different iterations. So what we did, we started with, this bounding in the 0th iteration, we started with 1.27 and 2.57, and then we generated this x1 and x2 according to the equation. Okay, and then we also had this f lower, f1, f2, and f of our computation. We found out which case, and in this case f2 was greater than f1, right? And then we determined the interval size, we determined the uncertainty percentage, and I showed you the equation to compute this uncertainty percentage that is there. Now since we know that this f2 is greater than f1, what we need to do, we basically need to move to the left hand side, right? So what in that case what will happen is essentially you will make x2 equal to x upper, you will make x1 equal to x2, and you will keep x lower as is. And that is what we did in iteration 1. And then what we'll do is we using the equation, and this is exactly what I showed you, using the equation we will compute these values of x1, and this is the computation that we have done in iteration 1. Now what we have now here is we can also now compute the f lower, f1, f2, and f upper in this iteration index 1, which is listed here. So in iteration 1 we have this x lower, x1, x2, and x upper, and if we sample the function values, we will have these function values, and then we can compare how f2 is doing with respect to f1, and in this case you will see that even in this case f2 is still greater than f1. So what we are going to do, we are falling there again in the second case or the otherwise case of the golden section algorithm, and what will happen in that case, we will make x2, which is there, as an x upper. We will take x1 and allocate that equal to x2, and we'll keep x1 lower, and then we will generate a new value of x1 using the equation that is there in the overall algorithm. So this is how you will move in a golden section algorithm that is out there. Now one of the things that I want to mention, that how many function evaluation we are doing, right? Initially, remember, when we started, we had x lower and x upper, and we have already sampled f lower and f upper. So in this first iteration, when we began, we did 2 more function evaluation, right? And this is how the overall algorithm started, right? So in this case, essentially we had some previous evaluations, but essentially if you look into incrementally from the iteration perspective, in each iteration only 1 more function values are evaluated and 1 more function sampling is done. So the actual number of function evaluations are in each iteration is essentially increasing by 1, even though initially when we begin we might have 4 or 5 function evaluations that are being done. So let's take this and extend this table further and look into even more iterations so that we can understand how the convergence will happen. Before I go into there, one of the other things that you want to see is as we are moving in the iteration, what is happening, we are computing this interval size and we are also computing this uncertainty. These values are reducing. Okay, so you will see as the iteration index is increasing from 0, 1, 2, and so these values are going to start shrinking and shrinking, and this is what is going to be used essentially as a stopping criteria. When these values are below a certain threshold or below a certain percentage, then we can stop the overall algorithm and we call that algorithm has converged and we stop there. But let's take and let's still expand this overall example problem, and let's see even more steps. Okay, so here is another steps, right? What was happening here? In this case, when we reach here, we fall into case 1 because f1 value was greater than f2 value. So if that's the case, what happens? We take the x1, which is right here, and we make that as x lower. Okay, so the x lower is equal to x1, so that's why this value comes here. Okay, we take x2 and make that equal to x1, so that's why we came here, and then we keep the x upper as is, and we sample, and using equation we find out a new value for x2 in this case, right? So that is what is defined by here. This 1.6877 is essentially determined by the equation for x2 given in case 1 of the golden section algorithm. Okay, so this is how the algorithm will move. And again, we did one more function evaluation. Again, the interval size and the uncertainty percentage is reducing, and this, as you will see, as we move on to further iterations, they are still going to shrink further and further, and then that is what is going to be used to stopping criteria. Yep. So let's move on here. And again, as I mentioned, the interval size and uncertainty computation that we have done in this table, they are important to keep track of because we are going to be using them as a stopping criteria, and we will stop the algorithm if these values are lower than the threshold. And for this example, the threshold has been set to equal to 5. So if either of this uncertainty value or the interval size value is less than 5, right, then we will stop this algorithm and we will take the x lower, x upper, and we'll average that, and that will be my optimal solution that we have. Okay. So let me continue this, computations and show you a table which has multiple other steps, right? So now you can see that you are moving, we've gone through 3, depending upon where each iteration, we are basically doing this function computations, and based upon that, we are determining whether we are in case 1 or whether we are in case 2, right? And we are switching between different things, and that is defined by the overall algorithm here. But now what I want you to focus on, if you look into this interval size and uncertainty value at iteration 8, or the iteration 7, this value was smaller than 5, or 3.44 or 3.33 is essentially smaller than 5, and this is where we will stop. And now we will take the value of x lower and x upper, and from there we will determine what is the optimal solution that we have. Okay, so the optimal solution, one of the simplest way to write the optimal solution could be the x optimal is essentially equal to x lower plus x upper divided by 2. And now recall, right, if your uncertainty value or the interval values are so small, essentially x lower will be very, very close to x upper. So this is one equation that you can use, or sometimes you can also basically allocate something like this, where x star is equal to x lower. And that itself could be a solution because this value and x upper value are not going to be drastically different that we have. Or we can take another solution where the x star is equal to x upper, right? And that also will be a solution to this overall problem because x upper and x lower are not drastically different because this uncertainty interval is very, very small. What has happened through the iterative process, right, which we are moving, we had like A and B initially very big, but they are shrinking and becoming smaller and smaller with each other, and eventually they will be very, very close to each other at one point of time, and that's where you will have this low values of interval size and low values of uncertainty, and that is what is basically used for this stopping criteria. So this is how the overall iterative scheme of golden section algorithm works. So I want you to focus on two major things that we want to understand from the golden section algorithm, right? Again, I want to repeat that golden section algorithm is just applicable for one variable optimization problem, and in practice what happens is you might not have essentially problems which are practical one variable, right? So you may have cases where you have multiple variables, and that will what you'll see in the practical problems. But by using the golden section algorithm, and even though we are focusing on single variable optimization problem, we have understood two main important concepts hopefully from this lecture, is that you can use an iterative scheme which is different than the analytical solution and then the graphical approach that we have discussed previously in the class, and you can use an algorithmic approach and an iterative fashion to also find out the solution of optimization problem, and that's what we have laid out in this problem, even though we focus on the single. So there could be a mathematical way or iterative fashion that could be devised to solve an optimization problem. That's one key takeaway. And the second thing that I want to focus is typically when we are using this mathematical approach or optimization approach or numerical approach to solve for this class of problem, we tend to use this stopping criteria that tells us when to stop. And these are the two fundamental things that you will see occurring in all the optimization algorithms, that is even applicable for higher number of variables going forward. Okay, so we will come back in the next class and we will discuss a completely new algorithm, but as you will see, it will have the same pattern. It will have some algorithm that iteratively changes the value, and we move in an iterative fashion to find where the optimal solution lies, and then it will have also a stopping criteria. And using these two concepts, we build a different algorithms that could be scaled to move away from single variable optimization problem to solve for multiple variable problem. Okay, with that we'll stop. We'll come back and take a new algorithm, still focusing on a single variable optimization problem, so that we can understand some intuitive aspect, and then going forward we will try to focus on multiple variable problems that we have. Thank you.